What is matter to begin with? Matter is anything that has mass and volume. Mass is the quantity of matter or the measurement of matter. Volume is the amount of space something takes up. So we can also say that matter is anything that has weight and occupies space. For example, this avocado is considered matter because it has weight and takes up a certain amount of space. How about this girl and her laptop? Are they matter? Yes, the girl is made of matter, so is her laptop, and so is everything else attached to her. These plants are also made of matter. This ocean, the sand, and all the animals that are here, these are all made of matter. Almost everything you can think of is matter, but there are a few things that are not matter. Those things are forms of energy, like light, heat, and sound. So what is not matter are forms of energy. Like the sun rays that give off heat and light, these are not matter. Lightning and thunder give off forms of energy like light and sound, and these are not matter. They are forms of energy. There are properties of matter that you should be familiar with, and properties just means like characteristics. So these characteristics of matter are color, size, volume, density, boiling melting point, solubility, reactivity, combustibility, flammability, and there really are more, but you get the point. So these can all be categorized as either a physical or chemical property, which we will be discussing later. Matter can be classified by its chemical composition, but also by its physical form. Physical form of matter is also called states of matter. I just like to use the word forms because I think it is a better interpretation of the concept. These are our three forms of matter, or states of matter: solid, liquid, and gas. Keep in mind that two things determine the state of matter. In other words, determines if an object or substance is a solid, liquid, or gas. One is how far apart the molecules are from each other, and two is how fast these molecules are moving. So let's look at a solid first. Molecules in a solid are tightly packed and don't have much room to move around. In fact, they have no room to move around. Instead, they vibrate in place. Because they are vibrating, they still produce kinetic energy, just at a very low frequency. It is important to know that because the structure of a solid is rigid and does not have movement, solids have both a fixed shape and fixed volume. Liquid molecules are spaced out and have more room to move around and bump into each other. The kinetic energy of a liquid is more than a solid, but less than a gas. Liquids have a fixed volume. However, the shape is able to change and manipulate the volume depending on what container they are in. So if you had, for example, 3 different size cups and poured the same amount of water into all 3 of them, the volume remains the same because it takes up the exact same amount of space, but the shape of the liquid is now changed. In a gas, molecules are even more far apart and move around freely and quickly. Because the molecules have so much room to move far and quick, this creates a high kinetic energy within the gas. Kind of like if you had a gas held in a container tightly, then you open the container, the gas might explode out of the container rapidly because of all the kinetic energy it has. For example, helium is one gas that has the most kinetic energy. It's used to fill balloons. If you've ever seen the balloons get full of helium, you'll notice that they fill up very quickly. This is because the helium gas is coming out of the container at a rapid rate. These states of matter go through changes we call phase changes. When a gas turns into a solid, it's called deposition. Solid to a gas is called sublimation. Solid to a liquid is melting. Liquid to a solid is freezing. Liquid to a gas is evaporation or vaporization. And gas to a liquid is condensation. Both temperature and atmospheric pressure regulate the phase changes. In other words, temperature and pressure are the 2 important factors that cause phase changes. As temperature increases, atmospheric pressure decreases. And as temperature decreases, atmospheric pressure increases. So now let's compare a heating curve and a cooling curve, which show the correlation between both temperature and heat absorption. In a heating curve, we have solid, liquid, and gas going upwards. We have heat absorbed here. As we go more to the right, more heat is absorbed. And of course, if heat is absorbed by the molecules, it means that temperature is rising as well. Here we have the first phase change that turns solid to liquid, which is melting. During the phase change, you can see that the molecules are absorbing more heat and the temperature is rising. This causes the molecules to spread apart from each other and move freely. As we go from a liquid to a gas, in other words, vaporization, the molecules are absorbing even more heat and the temperature is increasing even more. This creates a sort of expansion and the molecules spread out even further from each other, and they're basically able to move more freely and even more quickly than a liquid. Because the molecules are moving so quickly here, in a gas, the kinetic energy is very high. And of course, we can't forget solid to a gas is sublimation. So the molecules here are quickly going from vibrating in place to moving around freely and quickly. Again, just want to emphasize the main points on a heating curve during the phase changes, including melting, vaporization, and sublimation. The main points are molecules absorb heat energy. This results in an increase in temperature. The increase in temperature causes cohesion to decrease. And by the way, cohesion is kind of like the glue that keeps the molecules attached to one another. This decrease in cohesion lets the molecules spread apart from each other and move freely and quickly. So here's a quick visual of what the molecules would look like as you go up the heating curve from solid to liquid to gas. So remember, in a heating curve, molecules are absorbing heat and cohesion between molecules decreases. Now let's look at a cooling curve. In our cooling curve, the molecules are going to be releasing heat, and this is what's going to make them cooler. So here we have condensation. During condensation, molecules are releasing heat and getting cooler. This cooling of the molecules makes them more compact and come closer together. During freezing, the molecules are even more cooler and they are releasing even more energy, heat energy, and they are even closer, and now they're unable to move. So here the molecules vibrate in place. Lastly, we have deposition, where molecules are quickly going from moving free and quick to not being able to move at all, and they're stabilized and vibrating in place. During the phase changes of condensation, freezing, and deposition, molecules release energy, resulting in a decrease in temperature. This decrease in temperature causes cohesion to increase between the molecules, and it causes the molecules to come close together. As a result, they have no room to move. Here's a look at what the molecules would look like as they cool down from gas to a liquid and liquid to a solid. And just remember these three very important points from a cooling curve. The cooling curve involves gas, liquid, and solid going downwards as they cool off. Molecules are releasing heat here, and there is an increase of cohesion between molecules as they cool off. And here's a side-by-side in case you want to compare the two. Basically, the heating curve and cooling curve, they are doing the opposite thing. Lastly, we're going to go over chemical composition. We begin here with matter at the top, and matter can be described as either a pure substance or a mixture. A pure substance has the same chemical composition throughout its sample, whereas a mixture has various compositions throughout its sample. A mixture consists of two or more pure substances combined. A pure substance can either be broken down into an element or a compound. An element is what you find on the periodic table. These cannot be broken down into any simpler substance, even by chemical reaction. A compound is a substance combined of two or more elements in definite proportion. Let's look at some examples of elements and turn them into some compounds. So here we have oxygen, hydrogen, sodium, and chlorine atoms. These are all in their purest, most simplest form, their elemental form. Now we can combine these elements to make compounds. So if we combine hydrogen and oxygen, we can make H2O. If we combine sodium and chlorine, we can make sodium chloride. So remember that a mixture is two or more substances mixed together. In a homogeneous mixture, the composition remains the same in the entire sample. Or we can say that the composition is uniform throughout the sample. Also, there are no distinct boundaries, meaning you cannot easily see the substance separate from each other. Instead, all the substances are blended together. In a heterogeneous mixture, the composition varies, and there are distinct boundaries. In other words, you can clearly see a boundary line separating the substances. An example of a homogeneous mixture is salt water. If we mix salt and water in a cup, the substances blend in together, so we see a uniform composition, and there is no clear boundary line between salt and water. But if we take a magnified look, we can clearly see salt molecules and water molecules separate. Remember, what makes this a mixture is that we have two pure substances. In this case, salt is an element, which is a pure substance, and water is a compound, which is also a pure substance. Two pure substances combined together makes this a mixture. And what makes it homogeneous is the appearance of the substance is uniform. An example of heterogeneous mixture would be oil and water. Let's say here we have some boiling water and we add some oil inside. Eventually the oil and the water will separate because they don't mix. Oil will stay at the surface and water at the bottom. We can clearly see the boundary line between the two substances. That makes this heterogeneous. I want to remind you that what makes this a mixture is that we again have two pure substances combined together in one substance. The substance is everything in the pot. The oil is a compound, which is a pure substance, and the water is a compound, which is a pure substance as well. Hi everyone, welcome. Today we are going to be looking at a general view of the subatomic particles, atoms, elements, molecules, and compounds, specifically to understand their relationship with each other. Starting off with the smallest of them all, the subatomic particles. We have the proton, which has a positive charge, the electron, which has a negative charge, and the neutron, which has no charge at all. It is neutral. These subatomic particles are what make up your atoms. In the center of every atom is the nucleus, and this takes up the largest portion of the mass of an atom, particularly because there are neutrons here, and they have the largest mass of all the subatomic particles. Neutrons are the heaviest. Protons are also found here in the nucleus. Electrons can be found on these oval-looking rings surrounding the nucleus. These oval-looking rings are called orbitals. Now our atom is what makes up our elements, and our elements are all found on the periodic table. Elements cannot be broken down into any simpler substance, even by chemical reaction. That gives these their special place here on the periodic table. Each element is composed of one unique type of atom. So, for example, the element sodium is only made out of sodium atoms, iron is only made out of iron atoms, and bromine is only made out of bromine atoms. All the elements are made up of either one atom or two atoms. When referring to elements that are made out of two atoms, we call these diatomic. There are 7 diatomic elements, which include hydrogen, fluorine, bromine, iodine, nitrogen, oxygen, and chlorine. You'll notice the little 2 subscript after each elemental symbol. This means that there are 2 atoms that make up this element. Let's take a close look at a diatomic element and see what it would look like magnified. Take hydrogen, for example. If we were to look at a sample of hydrogen gas, we would see pairs of hydrogen atoms. In contrast, if we took a magnified look at an element that is not diatomic, like helium, for example, we notice all the helium atoms are by themselves. They are singular. Let's look at one more example. We have nitrogen on the left side and argon on the right. Nitrogen is our diatomic element, and argon is not. Nitrogen we see comes in paired atoms, and argon atoms are singular and independent from each other. Okay, so taking a step back, the diatomic elements can be further described as molecules because molecules consist of two or more atoms. They can be the same type of atom or they can be different types of atoms. By definition, you can see why all of the diatomic elements can be called molecules because they are all made of two atoms. However, all the other elements do not fit the description and they are not called molecules in their natural form. Natural form is referring to the elements straight off of the periodic table. So I must stress that this is in their natural form because they are capable of creating a molecule. That is when they are combined with other elements. So when they combine together, like in the second set of examples, they fit the description of a molecule. So the first set of examples are molecules of the same type of atom, and the second set of examples are molecules with different types of atoms. If you need a visual of the second set, I'm going to give you one in a minute. So these second set of examples that are circled here can be further described as compounds. A compound consists of two or more different types of atoms. So we can clearly see that this second row of molecule examples can also fit the description of a compound. Therefore, these molecules can also be called compounds. Let's take a magnified look at these compounds. Take, for example, NaCl. We see one sodium atom attached to one chlorine atom, and this together equals a molecule. That is also called a compound. It is a molecule because it's made out of two or more atoms, and it's a compound because it's made of two different types of atoms, both sodium atoms and chlorine atoms. And this sums up the relationship between subatomic particles, atoms, elements, molecules, and compounds. The periodic table displays all 118 known elements. Each element we know is made up of a unique type of atom. And because each element is made up of a unique type of atom, no two are the same. So we can conclude that each one will have different properties or characteristics. There are several ways to put these elements into categories, but we're going to go over the most important and the most common ways to categorize them. So first off, the elements are arranged in order of lowest atomic number to the highest atomic number. So starting from the top left, going down to the bottom right. So our lowest atomic number is hydrogen with an atomic number 1. And moving down the row, we have helium with an atomic number 2, lithium with an atomic number 3, beryllium with an atomic number 4, boron with an atomic number 5. And as we keep going down the list or down the rows from left to right, we will eventually reach our last element with the largest atomic number, number 118. Next, we have columns going down the periodic table. These are referred to as groups or families. There are 18 total groups. The elements in the same group share similar properties. So next we have the rows going horizontally, and these are referred to as periods. There are 7 periods total. So you might be looking at the bottom 2 rows and wondering, where do these go? Well, they're actually part of row 6 and row 7. Some periodic tables will put them at the bottom here just to save some space and make the periodic table look more compact. But if we look close, we see on row 6, there is a space here that says atomic numbers 57 and 71. So this space is reserved for the elements who have the atomic numbers 57 to 71. And if you look here, this atomic number of lanthanum is 57. So this row starting with lanthanum fits right here. Also, if we look at row 7, there is a space left here for atomic numbers 89 to 103, and that's exactly where this bottom row goes. We can also separate these elements by metals, nonmetals, and metalloids. Very important, if you look at the top left corner where there is a star, hydrogen is underneath it, and you'll notice that this hydrogen is a non-metal. However, what is it doing all the way on the other side with the metals? Well, it's there because it shares the same properties with that of the group 1A. So everything, all the elements here on group 1A, they're all going to have similar properties. That's why hydrogen is there, even though it's considered a non-metal. So let's take a look at the properties of metals, nonmetals, and metalloids, starting off with the metals. So these metals have a shiny luster. They are great heat and electrical conductors. For example, we have the metal in our wires that we use to transfer and conduct electricity. They are ductile, and that means that they are able to be compressed into a wire. They are malleable, meaning they're flexible without breaking. So like this guy here is hammering at his metal and reshaping it, and it's not chipping off and breaking. Metals are highly dense, and they have a high melting and boiling point. So this means that it takes a lot of heat energy to get them to a melting or boiling point. Lastly, they have tendencies to form cations, or in other words, atoms with a positive charge. Nonmetals are pretty much the opposite of metals. First, instead of being shiny, they are dull. They are poor heat and electrical conductors. They are usually brittle and easy to break, and they have a low density. They also have a low melting and boiling point, so it does not take a lot of energy to get them to a boiling or melting point. Also, they form both cations and anions. Lastly, the metalloids are like a fusion of metals and nonmetals, so they share properties of both. And just remember that these metalloids are found on what look like a staircase on the periodic table, which divides the metals on the left side and the nonmetals on the right side. So I made this chart here with a few other important properties relating to metals, nonmetals, and metalloids. I did it on a chart form so you can see the side-by-side differences, so you can go ahead and stop this video if you'd like and take a look at it. We can also categorize our elements by transitional metals and main group elements. Transitional metals are referred to as group B, which we aren't going to go over in this video because it's not relevant. And then we have our main group elements, which are referred to as group A. So our main group elements, group A, is everything you see highlighted in purple. And out of these groups, there are 4 very important ones you must remember. Group 1A are your alkali metals. Group 2A are your alkaline earth metals. And then if we jump over to the other side and skip 3A, 4A, 5A, and 6A, we'll go to group 7A, which are your halogens, and group 8A, which are your noble gases. So each of these groups, as mentioned before, have different properties from each other. So if we look at our alkali metals in group 1A, the most notable property is that they are highly reactive. And reactive just means that they interact well with other atoms. They also form cations with a positive 1 charge. So that means that all of the elements on this group 1A, underneath the alkali metals, they are going to form cations with a positive 1 charge. Alkali earth metals are also highly reactive, but not as much as alkali metals, and they form cations with a 2+ charge. Halogens, the most important thing you need to remember about these is that they are diatomic elements. And remember, diatomic means that in the element's natural form, it is made out of 2 atoms. Also, halogens form anions with a -1 charge. Lastly, our noble gases are the most stable and least reactive. They are also called inert gases. And what this means by least reactive and most stable is that their outer valence shell is completely full of electrons, making them stable and complete. First off, when looking at the periodic table, make note that these are all elements in their neutral form, meaning they have no charge. If we take a close look at one of these elements, let's just say carbon, for example, in the center is the element symbol. In this case, it's C for carbon. On the top, you'll find the atomic number. This number represents the number of protons in the atom. The atomic number is also the identification, if you will, for an atom. Each element has a different atomic number, and this number does not change. Next, on the bottom, we have the atomic mass. This is the average number of protons and neutrons for all of the isotopes made by this atom. The atomic mass is similar to the mass number. Mass number is the number of protons and neutrons in the atom. This number is a whole number. To get the mass number, you just have to round the atomic mass to a whole number. So for carbon, we can round it up to 12, and 12 is our mass number. So that's how the element is shown on the periodic table. But more than likely, on an exam, you will be asked to write or show the elemental symbol. This is how we do that. Using carbon again as an example. We write the elemental symbol first. On the top left, we write the mass number. And on the bottom left, we write the atomic number. So you can see here, things are kind of flipped. And there you have it. This is the correct way to write out the element carbon. So what is a neutral atom? Or what makes an atom neutral? Neutral atoms are what you find on the periodic table. They have the same number of protons as they do electrons. And they have no charge. They are neutral. Let's take this carbon for example. What makes this carbon neutral? We know it has 6 protons because we can see it has an atomic number of 6. And because it is neutral, it has the same amount of electrons as it does protons. The positive and negative charges cancel each other out, and what's left is a neutral atom. Let's look at another example. On an exam, you will most likely see something worded kind of like this, where they ask you to find the number of protons, electrons, and neutrons in an atom with this given information. Here, the given information is the element calcium. We know it has 20 protons because it has an atomic number of 20. We know it has 20 electrons because it is a neutral atom. Same number as protons. And now to find the number of neutrons, we take the atomic mass and subtract the atomic number. Because the atomic mass is the number of protons and neutrons, and the atomic number is the number of protons. So we are left with the total number of neutrons, which happens to also be 20 in this case. Let's do another example using aluminum as our given information. Given the atomic number, we know aluminum has 13 protons and 13 electrons because it's neutral. Now round the mass up to 27 and subtract 13, we are left with 14 neutrons. By the way, are you able to find the atomic mass and the mass number? Remember, the mass number is a whole number and is the number of protons and neutrons, while atomic mass is a bit more complicated. It's a decimal number and it's the average of the protons and neutrons in the isotopes. So the atomic mass is 26.982, and that is given on the periodic table. And the mass number is just rounded up to 27. So we've gone over neutral atoms. Now let's go over ions. What is an ion? An ion is an atom with a charge. An atom gets a charge when it gains or loses electrons. An ion either has more protons than it does electrons, in which case it's called a cation with a positive charge, or it has more electrons than protons, in which case it's called an anion with a negative charge. The golden rule that you must never forget about ions is ions will always have the same number of protons as the atomic number. In other words, the number of protons never changes. You can only change the number of electrons because remember, in the definition I mentioned, an atom becomes an ion by either gaining or losing electrons. So we're only manipulating the electrons, not the protons. So let's say we have an atom here and the plus sign represents protons because they have positive charges. And the negative represents electrons. So this atom here has 6 protons and 4 electrons. These pairs cross each other out and we are left with 2 extra protons. That makes this atom a cation with a +2 charge. Next, we have an atom here with 4 protons and 7 electrons. These pairs cross each other out, and we're left with 3 extra electrons. That makes this atom an anion with a -3 charge. This next example is how you will most likely see it on an exam. They give you information on the number of protons, electrons, and neutrons, or just protons and electrons because neutrons isn't too relevant here. And then you have to find the charge of the ion. So given the following information, write the charge for the following ion. So here we have 12 protons, 9 electrons, and again, the number of neutrons has no relevance to this question, so you could just forget about it. The pairs cross each other out, and we're left with 3 extra protons. That makes this a cation with a +3 charge. Next, we are given the following. Write the charge for the following ion. We have 9 protons, 10 electrons. Already we can say that this will be an anion because it has more electrons than it does protons. We are left with an anion with a -1 charge, or you can just put negative. The 1 is always implied, so you don't necessarily have to have the 1 there. So lastly, I just want to leave you with the trends of ions on the periodic table. So quickly, the group 1A, where you see the 1 plus or the 1 positive above, all of these elements will form a 1+ charge. So that includes hydrogen, lithium, sodium, potassium, and everything else on that row. Group 2A will form cations with a 2+ charge, and that includes everything on that row. And then transitional metals, it varies. More than likely, this is upper division chemistry, so don't worry about that. And then so on. So it's very important that you know that this is a general guideline to what what elements form these ions. So there are some exceptions to this rule, but this is a good start to remember the ion numbers on the top of the periodic table, because this can seriously save your life on an exam, remembering these numbers at the top, and of course, they're negative or positive charges. Atoms either lose, gain, or share electrons. This is what forms a bond between 2 atoms. Atoms form bonds in order to satisfy the Octet Rule. The Octet Rule states that elements combine in such a way that each atom has 8 electrons filling their valence shell. In order for this to happen, each atom must give up or gain or share electrons. We know that the valence shell refers to the outermost shell on an atom, and the valence electrons are all of the electrons on that valence shell. So 8 electrons filling up the valence shell is going to make these atoms very, very happy. The elements highlighted here are our noble gases, and all elements strive to become like the noble gases. They look up to the noble gases because these noble gases are the most stable elements, because they naturally have a full valence shell. They naturally have 8 electrons filling up their valence shell, with one exception. That exception is helium. It only has 2 electrons in its valence shell, and it doesn't strive to be like all the other elements. It is perfectly fine with only having 2. Metals lose electrons because they have fewer electrons in their outer shell. So because they have fewer electrons in their outer shell, it makes it easier for them to just lose a couple rather than gain a bunch. You will clearly see this once you see some examples. So here we have potassium as an example, and potassium has 19 electrons total. Notice it only has 1 valence electron in that valence shell. So because potassium is a metal, it is going to lose this 1 valence electron. Once that electron is lost, the shell is now empty. Therefore, potassium really doesn't need this shell, and it's basically going to disappear. Once that shell disappears, the shell underneath actually has 8 electrons, and this is now going to be the new valence shell. Because potassium lost 1 electron, that means it has not 19, but 18 total electrons now. So potassium with 19 protons and 18 electrons creates a cation with a +1 charge. So the takeaway here is metals lose electrons because they have fewer electrons in their outer shell. Also, metals form cations, which are ions with a positive charge. Non-metals, on the other hand, gain electrons because they have more electrons in their outer valence shell. For example, we have fluorine here and it has 9 total electrons. Notice it has 7 valence electrons. Here we have this atom floating by and it has 1 valence electron. It's actually going to give this valence electron to fluorine. And now fluorine is going to have a full valence shell. It has 8 electrons or 8 valence electrons in its outer shell. And now fluorine is happy. So just like we did with the metals, we now have to look at the total number of electrons and adjust it. Fluorine has gained 1 electron, so now it has a total of 10 electrons, not 9. Fluorine has 9 protons, and again, that's never ever going to change because remember, the number of protons will never change in an atom. But now it has 10 electrons, so this creates an anion with a -1 charge. The takeaway here is nonmetals gain electrons because they have more electrons in their outer shell. Nonmetals also form anions, which are ions with a negative charge. So notice that this is the exact opposite of metal characteristics. Now that we understand how metals and nonmetals work when they create a bond, let's see exactly how they create ionic bonds. Ionic bonds will have a metal and a nonmetal bonded together. The atoms that form ionic bonds will either lose or gain electrons, and this is referred to as a transfer of electrons. Here we have sodium and chlorine atoms. Sodium is our metal, chlorine is our nonmetal, so automatically we know we have an ionic bond because we have a metal and a nonmetal coming together. Now you know that if you ever see a metal and nonmetal together, you know automatically it's going to be an ionic bond. Our sodium has 11 protons and 11 electrons, and our chlorine has 17 protons and 17 electrons. Sodium would look a bit like this, and chlorine would look like this. Notice sodium, our metal, has only 1 electron on its valence shell, and chlorine, our nonmetal, has 7 electrons on its valence shell. So again, our metal is going to lose its electron and our nonmetal is going to gain electrons during this ionic bond. This little guy is going to make its way over there, and that is a transfer of an electron. Now notice sodium has a shell that has no electrons on it, so it doesn't need the shell. It's going to completely lose it, and underneath it, it has a nice 8 electrons in that new valence shell. So sodium is happy, and chlorine is also happy because it also has 8 electrons in its valence shell. There is one last thing we need to adjust after filling up these valence shells. On the metal, we have lost 1 electron, so now sodium doesn't have 11 electrons, it now has 10. This sodium turns into a cation with a +1 charge. Chlorine has gained 1 electron, so it doesn't have 17 anymore, it has 18. Chlorine is now an anion with a -1 charge. So sodium is our positively charged atom and chlorine is our negatively charged atom. As we know, opposites attract. So this is what keeps ionic bonds together. It's that attraction of opposite charges. Metals are generally least electronegative and nonmetals are most electronegative. Because nonmetals are more electronegative, it means that they are better at attracting electrons towards them. So nonmetals will always attract electrons from the metals. That's why they gain electrons and metals are the ones that lose the electrons. So let's go ahead and move on to covalent bonds. Here we're going to work with 2 nonmetals bonding together. Atoms that form covalent bonds share electrons, so there is no transferring electrons here. One atom is not going to lose or gain electrons. Instead, these atoms are sharing these electrons. One thing important to remember is that all diatomic molecules have covalent bonds between the same atoms. And if you need a reference, remember, these are all of your diatomic molecules listed here. For example, here we have nitrogen, and let's just say another nitrogen comes along, and that nitrogen says, hey, want to get together so we both have a full valence shell? Heck yeah, let's get together and become diatomic molecules. So they come together, they become diatomic molecules, and the both of them live happily ever after. All of these diatomic molecules are going to look very similar to this nitrogen. They're going to form a bond that is covalent between them. Let's look at an example of covalent bonds that is not between diatomic molecules. Say, for example, CO2. For the sake of simplicity, I'm only going to draw the valence shell with the valence electrons. So just want to let you know that so you don't get confused. Not all of the electrons are going to be drawn on these atoms. So here we have the carbon valence shell, and these are our two oxygens valence shells. Notice that the oxygen has 6 electrons in its valence shell, and carbon has 4 electrons in its valence shell. Remember, these atoms have one goal in mind, and that's to fill up their valence shell with 8 electrons. So carbon is going to take 2 electrons and share it with both of the oxygen. And oxygen is also going to take one of its electrons and share it with the carbon. So now this is all rearranged, and we'll notice that oxygen now has 8 electrons filling its valence shell. And carbon also has 8 electrons filling its valence shell. So all atoms are happy with full shells. Now let's see how electronegativity relates to the covalent bonds. In a covalent bond, one atom will always be slightly more negative than the other. And of course, that means that the other atom will be slightly more positive. Now, the key word here is slightly, because if they were completely negative or completely positive, that would make them have charges, and that would mean they were ionic. The atom that is more electronegative will be the more negative atom. This atom, of course, attracts more electrons around it. And in case you need to refresh your memory, this is the electronegativity trend on the periodic table. Remember, fluorine is our most electronegative atom. As we go from left to right or towards fluorine, the electronegativity increases. And as we go up the periodic table, electronegativity also increases. If we use our example of hydrogen and chlorine bond, if we look for both of these atoms on the periodic table, we will notice that chlorine is obviously more electronegative. Therefore, it attracts more electrons around it, and this makes chlorine partially negative. We're going to represent this partially negative with a delta sign and a negative sign after it. By the way, delta means slightly, so slightly negative. And hydrogen is less electronegative. It has less electrons around it. This makes hydrogen partially positive. And we're going to represent this with the delta sign again and a positive sign, so slightly positive. Let these delta signs be a reminder that these atoms are not ionic. They are not fully positive or negative. They are just slightly positive and slightly negative. Remember, delta means slightly. When the difference in electronegativity between two atoms is equal to or more than 0.5, this is called polar covalent bond. So let's use our example of hydrogen and chlorine. Normally you will be given the electronegativity value. Here hydrogen has a value of 2.1 and chlorine has a value of 3.0. So this is how we calculate the difference between the two values. We basically just subtract them and we'll end up with 0.9. 0.9 is the total difference in electronegativity between hydrogen and chlorine. In order for this to be a polar covalent bond, the electronegativity difference between the two atoms must be equal or more than 0.5. So because the electronegativity difference between hydrogen and chlorine is 0.9, the two atoms form a polar bond or a polar covalent bond. If the electronegativity is less than 0.5, the covalent bond is nonpolar. Although there is still one atom that is slightly more positive and the other is slightly more negative, the difference is still not significant enough to call it polar. Let's take, for example, these hydrogen atoms. The electronegativity value is 2.1, and of course, it's the same value for both atoms because they are the exact same atoms. Because the electronegativity between both atoms is the same, there is an equal sharing of electrons between the two. This goes for any diatomic molecule like oxygen, fluorine, and all of the other diatomic molecules. They will have a non-polar covalent bond. Let's go ahead and finish off with some practice problems. Here we have hydrogen attached to another hydrogen. Is this an ionic bond, a polar covalent bond, or a non-polar covalent bond? The first thing we want to look at is automatically rule out if this is an ionic bond. If it's an ionic bond, it will be a metal and a non-metal. Hydrogen is a non-metal, so this is actually non-metal and non-metal, so it's not ionic, it's covalent. Now let's determine if it is a polar or non-polar covalent bond. Because it is a diatomic molecule and is the exact same atom attached to each other, that means the electronegativity is exactly the same. So this is a non-polar covalent bond. How about carbon and hydrogen with the values of 2.5 and 2.1? This is a non-polar covalent bond because if we look at the difference between the two electronegativity values, we get 0.4. Remember, polar is any difference of 0.5 or more. So because it's only 0.4, it makes this bond non-polar. How about calcium and sulfur? Calcium is a metal and sulfur is a non-metal. Therefore, we know automatically we have an ionic bond. What about oxygen and hydrogen with values of 3.5 and 2.1? If we find the difference of the two values, we get 1.4, which is going to make this a polar covalent bond. What about H2O? Now, I added a little extra stuff here just to make it look a little more complicated, but that's just the reality. You might see something like this on your exam. Focus on the electronegativity values and find the difference of the values. The electronegativity difference here is 1.4, so that's going to make H2O a polar covalent bond. By the way, we automatically ruled out ionic bond because hydrogen and oxygen are both non-metals. Also, I want to introduce this symbol here called a dipole moment. The arrow points in the direction of the most electronegative atom. In this case, both arrows are pointing in the direction of the oxygen. Next, we have nitrogen bonded to nitrogen. We know this is a diatomic molecule, therefore we automatically know it's a non-polar covalent bond. Next, we have NaCl. Sodium is our metal, chlorine is our non-metal, so we have an ionic bond. How about magnesium oxide? Again, magnesium is our metal, oxygen is our non-metal, so we have again an ionic bond. So here we have an atom and the things circulating around it are representing three-dimensional spaces that we refer to as energy levels or shells. Orbitals reside in the energy levels and electrons reside on these orbitals. If we freeze this atom, it would look something like this. The nucleus of an atom in the center with X for now representing the element. Surrounding the nucleus, we represent the energy levels with these rings. Here we have 3 rings, so we would say that this atom has 3 energy levels. We also have electrons. These electrons hang out around these energy levels. We always fill these energy levels starting with the innermost, then working our way out towards the outermost. So we fill up the innermost and then we go on to the next shell. The first energy level can only hold 2 electrons. The next can hold up to 8 electrons. The third can hold up to 18. The outermost energy level is referred to as the valence shell. And the electrons on this valence shell are referred to as valence electrons. Valence electrons are super important because the number of them determines the atom's ability to interact in chemical reactions. These valence electrons are going to be doing all of the interaction and communication with other atoms. It's very useful to have a quick reference to the number of valence electrons an atom might have. So if we look at the periodic table, we have 2 important parts here. First, we have the period number, which is going to tell you how many energy levels or shells an atom has. Then we have the groups, which is going to tell you how many valence electrons an atom is going to have. And unfortunately, this is excluding the transitional metals. The transitional metals are just not as predictable. So our periods are numbered 1 to 7, and the groups are numbered 1 to 18. Now, there is an adjustment we need to make in the groups. Instead of numbers 13, 14, 15, 16, 17, and 18, we are actually going to turn these into 3, 4, 5, 6, 7, and 8. And this is because the maximum number of electrons in the valence shell can only be up to 8, not 18. Okay, so let's go ahead and look at an example like hydrogen. Here's the nucleus of the hydrogen atom. Because hydrogen is in period 1, we know it will have only 1 energy level. And because it is in group 1, we know it will only have 1 valence electron. Next, let's look at lithium. Lithium is in period 2, so it will have 2 energy levels, or we can also call them shells. It is in group 1, so we know it will only have 1 valence electron. How do we know how many electrons lithium has? We know this because the atomic number is 3. And since the number of electrons is equal to that, we are going to fill this atom with 3 electrons. 2 in the first shell and 1 in the valence shell, or the last shell. So next, let's look at calcium. Calcium is in period 4, so we know it will have 4 shells. 2 electrons will fill up the first shell, 8 will fill up the second shell, and now we have to use some critical thinking to fill out the third shell, because we know the third shell has a capacity to fit 18 electrons, but we must only fill it with 8. We know this because the periodic table tells us calcium must have 2 electrons in its valence shell. In order to accommodate this, we must place 8 in the third shell, so we have 2 left over for the valence shell. Okay, so with that being said, these are the rules to how many electrons can fit in each shell. We've gone over a few, like 2 electrons in the first shell, 8 in the second shell, 18 in the third shell, 32 in the fourth shell, 50 in the fifth shell, 72 in the sixth shell, and 98 in the seventh shell. So mostly you just have to worry up to energy level 5 because most questions are asked regarding the elements that go up to energy level 5. So one last example using xenon. Xenon is in period 5, row 8, and has 54 electrons. First shell, we fill up with 2 electrons. Second, we fill up with 8 electrons. Third, we fill up with 18 electrons. Now the fourth, we technically have a capacity of 32. However, we need to have 8 electrons in that last shell, the valence shell, right? So we must accommodate this by placing only 18 electrons here in the fourth shell, so that we can finish off with 8 in the valence shell. So altogether, if we count these electrons, 2 plus 8 plus 18 plus 18 plus 8, we get a total of 54 electrons. So I just want to emphasize, if you were to fill up the fourth energy level with 26 electrons and basically not accommodate it, then the valence shell, that being the fourth energy level, would be totally incorrect, right? Because according to the periodic table, xenon should have 5 shells and 8 electrons on that last shell. So one last thing I want to add, the group 8 elements all have 8 valence electrons. And that's totally normal, but there is one exception, and that exception is helium. Helium actually only has 2 electrons, so it can only have 2 valence electrons, not 8. Isotopes are various forms of an element. If an element was a car brand, the different models or styles it comes in would be the different types of isotopes. They look a bit different and have different characteristics, but the one thing they have in common is that they originate from the same brand. So the isotopes may look different and have different characteristics, but they originate from the same type of atom. We know that the number of protons is the signature of each atom. Each atom will have different number of protons. So carbon will always have 6 protons, oxygen will always have 8 protons, hydrogen will always have 1 proton, and so on. So all isotopes of the same atom will always have the same number of protons. The thing that changes with isotopes is the number of neutrons. And because the number of neutrons changes, the mass number will also change, because remember, the mass number is the total number of protons and neutrons in each atom. So of course, the change in the number of neutrons will also reflect the mass number. Let's take carbon for example. This is carbon right off of the periodic table, so it is in its original form. We know it has 6 protons. It has 6 electrons because we know it's neutral. We know it's neutral because the example is right off the periodic table. Also, there is no indication otherwise. We know it also has 6 neutrons. We calculate this by subtracting the atomic number by the mass number. I'm going to show you what this would look like in regular notation so you can compare it side by side to isotope notation. So we start by putting the elemental symbol, followed by the mass number at the top and atomic number at the bottom. Now let's compare this carbon in its regular form to carbon in its isotope form. So carbon has various isotopes, too many to write down, but I'm going to give you an example of carbon-13 and carbon-14. Both are isotopes of carbon. We can write an isotope in 2 ways. One is by writing the element, then adding a dash, followed by the mass number. The other way is writing the elemental symbol, the mass number at the top, and the atomic number at the bottom. Notice that the atomic number remains 6, because remember, the atomic number never changes. It is the element's signature, and if carbon did not have 6 protons, it would not be carbon. Notice our mass number changes to 13. What influences the mass number? The number of protons and neutrons, right? So if the number of protons didn't change, that means that the number of neutrons in this atom did change. So remember, 2 ways of writing an isotope. Let's look at the isotope carbon-14. We can write it out like this. Right off the bat, we know this carbon has a mass number of 14. We can also write it like this, with the mass number of 14 on top and the atomic number of 6 at the bottom. So looking at the original carbon on the left, the 6 protons and 6 neutrons is what make the mass number 12. So just keep this in mind when we do a count of neutrons and protons of the isotope. Starting with carbon-13, we have 6 protons because the atomic number is 6. We have the same amount of electrons because this is a neutral atom. We find the number of neutrons by subtracting 6 from 13 and we get 7. So 6 protons and 7 neutrons is what gives us a mass number of 13. Looking at carbon-14, we have 6 protons, 6 electrons, and to find the number of neutrons, we subtract 6 from 14, and we get 8 neutrons. So the 6 protons and 8 neutrons is what gives us the mass number of 14. Let's finish off with a few practice problems. I've written each practice problem in the 3 different ways you can see isotopes written. So the first way is in isotope notation. All the information you need to find the number of protons, electrons, and neutrons is given right here. We know the atomic number is 92, so the number of protons is 92. Number of electrons is the same, 92. And to find the neutrons, we subtract 92 from 238 and we get 146. Next, we have sodium, and the mass number is given, but we're missing the atomic number. Simply, we look at the periodic table, find sodium, and see that the atomic number is 11 given here. Keep in mind, if you were to get a problem that looks like this, you will likely be given a part of the periodic table to find the atomic number. Atomic number is not something you are expected to memorize. Okay, so we have 11 protons, 11 electrons, and 12 neutrons. Lastly, we know this is an isotope because the way it is written. Specifically, it has a dash with a number at the end that does not match the mass number of hydrogen on the periodic table. Also, we see the atomic number on the periodic table is 1. So with this information, let's fill out the number of protons, electrons, and neutrons. Protons, we have 1 electron, 2 neutrons. Periodic trends refer to various patterns seen on the periodic table that help us visualize correlations of the elements. Before we jump into atomic radii, we must first understand a few basic concepts. For one, there are two factors that affect the atomic radii or size. One is the distance of the valence electron or electrons in the outermost shell and the proton within the nucleus. The second is the amount of protons in the nucleus. Both of these influence the force of attraction between the protons and electrons. Force of attraction is very strong between protons and electrons. However, the attraction between same charges is weak. So weak that in fact they repel each other. So positives with positives, they will repel each other. Negative with a negative will also repel each other. You can think of the proton in the center of the nucleus like a magnet, and it wants to grab the electron and bring it close to the nucleus. It would make sense to say that the closer an object is to the magnet, the better hold the magnet will have on it. So with that being said, the further away an electron is from the proton, the less attraction there is. And the less attraction there is, the less hold the proton will have on the electron. In contrast, the closer the electron is to the proton, the more attraction there is. And the more attraction there is, the more hold the proton will have on the electron. Next, the amount of protons in the nucleus will also greatly impact the force of attraction between the proton and the electron. The more protons there are, that magnetic attraction will be amplified. The more power the protons will have over the electrons, and they will be able to pull them in towards the nucleus. Okay, so we know now that two major factors influence the hold between protons and electrons. So now let's take a close look at atomic radii. Atomic radii is the size of an atom. Specifically, it is the distance from the center of the nucleus to the outermost electron. The trend of atomic radii on this periodic table looks like this. From right to left, it increases. In other words, the atoms get bigger going right to left. And going downwards on the periodic table, the atomic radii also increases. The reason why it increases going downwards is as you go down, the number of shells increases on the atom. We know that atoms on period 1 have 1 shell, period 2 have 2 shells, period 3 have 3 shells, and so on until we get down to period 7 with 7 shells. So, for example, on period 1, we have hydrogen with 1 shell. Period 2, we have lithium with 2 shells. Period 3, we have sodium with 3 shells. Period 4, we have potassium with 4 shells. Period 5, we have rubidium with 5 shells. Period 6, we have cesium with 6 shells. And I could not fit it here, but on period 7, we would have francium with 7 shells. So we can see that the atoms grow larger as they go down the periodic table. Now let's compare the atoms right to left and see why they get bigger towards the left side. Take hydrogen and helium, for example. Hydrogen has one proton in it in the center in the nucleus and one electron around it. Helium has two protons in the center and two electrons around it. Remember, we learned that the more protons an atom has, the stronger it will have a hold on the electrons. So the more protons created even more magnetic power that pulls these electrons towards the nucleus. This created a more compact and smaller atom. Versus a hydrogen atom that only has one proton, it will have less of a pull on the electron. Let's compare lithium and neon. Lithium has 3 protons and 3 electrons. Neon has 10 protons and 10 electrons. Simply because neon has more protons, it will have a greater pull on the electrons and bring them closer to the center, making this little neon more compact and smaller than lithium. Let's try a practice question. Which of the following has a larger atomic radii, potassium or sodium? Because potassium is lower than sodium, it has a larger atomic radii. How about oxygen and fluorine? Oxygen has a larger atomic radii. Associated with atomic radii is ionic radii. Ionic referring to ions like cations with a positive charge and anions with a negative charge. Here we have lithium in its neutral form and its ionic form with a +1 charge. Lithium has 3 protons in both forms. In its neutral form, it has 3 electrons, and because it has a 1+, it must have only 2 electrons in its ionic form. You will automatically notice that the cation is smaller than its neutral form. That is because cations will always have more protons than electrons. This creates a much stronger energy pull coming from the protons, and they're able to pull the electrons closer to the nucleus. In contrast, we have an anion. Nitrogen in its neutral form and in its ionic form as an anion with a -3 charge. Both have the same number of protons, that being 7. The neutral nitrogen has 7 electrons, while the ionic form has 10 electrons. There always will be more electrons than protons in anions. So the protons don't have the upper hand here. They do not have enough energy to pull these electrons inwards significantly. As a result, the anion stays larger in size simply because it has more electrons taking up space. The takeaway here is that if you are presented with a question involving ionic radii, remember, cations are smaller than their neutral atom, and anions are larger than their neutral atoms. Moving on to our next trend, ionization energy. Ionization energy is the energy required to remove one or more electrons from the valence shell of a gaseous atom. Here we have 2 atoms. One atom has its electron relatively far from the nucleus, and the other has its electron relatively close to the nucleus. We know that there will be a weak hold on the one that has a greater distance between the electron and the proton, and a strong hold on the one that has the electron closer to the proton. If another atom comes around and wants to create a bond with this atom to the left, will it have a hard time taking away its electron? No, it will not be hard at all. It will be so easy for another atom to come and steal away this electron because the proton in the center has a very weak hold on it. So if it is easy to take the electron, then less energy is needed to steal it away. Think of it like if you're trying to take a ball out of someone's hands and the person is weak. It won't take that much energy for you to steal the ball away from their grip. On the other hand is the proton that has a strong hold on the electron. When another atom comes along to steal the electron, it will be so hard for them. They will need more energy to steal the electron away. So if you're now trying to steal the ball away from someone who is a lot stronger than you, you will have to use way more energy, way more strength to try and steal it away from their grip. The takeaway here is the more energy needed to steal a valence electron, the more ionization energy increases. And the less energy needed to steal a valence electron, the ionization energy decreases. The trend on a periodic table goes like this. As you go up the periodic table, the ionization energy, or IE for short, increases. And as you go left to right, the IE also increases. So generally, it increases going in this direction. Let's look at an example. Which of the following has more ionization energy, hydrogen or helium? By relying on the periodic table, we can see helium is further to the upper right. Therefore, it has more ionization energy. That just means that it takes more energy from another atom to come around and steal its valence electrons. And it takes very little energy for another atom to come around and steal hydrogen's valence electrons. How about arsenic and selenium? Selenium has more ionization energy here. How about rubidium and potassium? Potassium is our answer here. Now, unfortunately, there are a few exceptions. I'm only including these because I know a variety of students will be using this video to study. So if you are in high school or college chemistry, you do need to know these exceptions. However, if you are here strictly for the TEAS exam, in my opinion, you don't need to know these, so just hang in there for a minute. These exceptions involved beryllium, magnesium, and calcium, also boron, aluminum, and gallium. Normally, we would say the elements on the right side have more IE, but we are going to flip them. So the correct way is beryllium has more IE than boron, magnesium has more IE than aluminum, and calcium has more IE than gallium. And just a few more exceptions. You're also going to flip these that I've circled. So nitrogen has more IE than oxygen, phosphorus has more IE than sulfur, and arsenic has more IE than selenium. By the way, if you're wondering why this is, I'm not going to go over it in this video, but if you know how to do electron configuration, go ahead and do the electron configuration for one of these examples and you'll see why you need to flip them. Okay, so moving on to our very last trend on the periodic table, electronegativity. Electronegativity is the tendency of an atom to attract electrons to form a chemical bond. Before we move forward, I think it's helpful to see a side-by-side definition of electronegativity and ionization energy because these two can easily be confused. Notice that the key word in electronegativity is attract electrons. And in ionization energy, the key word is to remove electrons. So this is what the electronegativity trend looks like on the periodic table. Fluorine is our most electronegative atom. So electronegativity increases going towards fluorine. It also increases going up and going from left to right on the periodic table. Let me explain why this trend happens. On the left side of the periodic table, we have our metals, and to the right, we generally have our non-metals. One of the characteristics of metals is that they like to give away electrons. Because they like to give away electrons, they lean towards being less electronegativity. You can also say that they are more electropositive. If we look at the definition again, electronegativity is an atom attracting electrons. So metals do the opposite. Non-metals, on the other hand, like to attract electrons. So they definitely lean towards being more electronegative, per the definition of electronegativity. One thing important to add here is that noble gases do not participate in electronegativity because they have a full valence shell and are completely content. They have no desire to give or take electrons. Let's look at some practice questions. Write the correct order for the following from increasing electronegativity. Increasing order means from least to greatest. So we have silicon, magnesium, chlorine, and aluminum. Our answer here is magnesium, aluminum, silicon, and chlorine. Magnesium being the least electronegative and chlorine being the most electronegative. How about silicon or oxygen? Oxygen is closer to fluorine, so it is more electronegative. How about silicon or carbon? Carbon is going to be more electronegative because it is above silicon. How about nitrogen and sulfur? Both look almost equidistant to fluorine, but nitrogen is going to be more electronegative here. The general rule is going up 1 unit is more electronegative than going to the right 1 unit. So going 1 unit up from phosphorus to nitrogen, there is more electronegativity than going from phosphorus 1 unit to the right to sulfur. Before learning how to balance chemical equations, we must first understand how it relates to a chemical reaction. A chemical reaction is when one substance or more converts into a completely new substance or substances. During this chemical conversion, bonds are broken and created between new molecules and atoms. This forms completely new substances. Chemical equations represent these chemical reactions taking place. One of the most crucial concepts to remember about chemical equation is their balance. The law of conservation of mass states that mass is neither created nor destroyed, even by chemical reaction. Therefore, a chemical reaction neither creates nor destroys atoms. It only transforms the existing atoms into something new. I like to think of it like Legos. So say you have 25 different pieces of Legos and you built a horse out of it. Then you took it apart and decided you wanted to build a dog out of the same exact Legos. You built both these things out of the same matter, the same object, and really it was built out of the same atoms. In the same way, atoms will be transformed from one chemical to the next. Atoms will transform to build different chemicals, but the atoms themselves remain the same. Because atoms are not created nor are they destroyed, the number of atoms of each element remain the same on both sides of the equation. Also, the number of moles remains the same on both sides of the equation for each element. We have two sides of a chemical equation. We start on the left with the reactants. These are the substances or substance you start with. The yield symbol indicates a chemical reaction has taken place. And on the right, we have the product, which is the substance or substances we end up with. Let's work out a few examples. So keep in mind that balancing chemical equations is a trial and error process, and it's going to require a bit of patience. But the more you practice, the quicker you will become and the better you will become at it. Starting here with zinc and hydrochloric acid on our reactant side, this yields zinc chloride and hydrogen on the product side. Remember, atoms are neither created nor destroyed according to the law of conservation of mass, so the number of atoms for each element must be the same on both sides of the equation. But they're not right now, so what can we do? Well, we can balance this chemical equation out. Starting with zinc, it looks like we have one zinc atom. We know this because the number in front of each element or molecule indicates how many atoms it has. No number means the element or compound has one atom. So we have one zinc atom here, one hydrogen atom, and one chlorine atom. On the product side, we have one zinc atom, we have two hydrogen atoms, indicated by this number 2 subscript, and we have two chlorine, indicated by this number 2 subscript, that is attached to it. So our zinc looks like it has a 1-to-1 ratio and it's balanced, so that's great. Hydrogen, however, is not balanced and chlorine is not balanced. Now, I want to point out something very important. The area that I have circled is called the coefficient, or basically it's where the coefficient goes. When manipulating numbers on the equation, you may only change these coefficients. The numbers down here, the subscripts, you must never ever change these. If you change these subscripts, then you're going to change the entire compound. Okay, so let's start by attempting balancing out hydrogen. We could put a coefficient of 2 here, and that will give us a 2 hydrogen. So hydrogen is now balanced. Now this coefficient is going to also be multiplied with the entire compound. So in other words, the 2 is going to be multiplied by every single element attached to it. So we multiply it by hydrogen, but also by chlorine. This will give us 2 chlorine. And now chlorine is balanced out. So now we have the same number of atoms of each element on both sides of the equation. And it's abiding by the law of conservation of mass, meaning we have the same amount of atoms of each type of atom on both sides, also meaning we have the same amount of mass or the same number of moles of each atom on both sides. Next, let's try phosphorus plus chlorine yields phosphorus pentachloride. Starting off with phosphorus, we have 4 phosphorus indicated by the subscript. We have 2 chlorine, and I want to point out here that we have a compound of pentachloride together. This compound is made of 2 different elements, both phosphorus and chloride. It might be tempting to multiply the number 5 to the phosphorus, but this would be totally wrong. The number 5 only belongs to the chlorine. The subscript only belongs to the element it is attached to, unlike the coefficient, which is applied to every atom or every element in the compound. That being said, phosphorus has 1 mole or 1 atom, and chlorine has 5 moles or 5 atoms. These phosphorus are unbalanced, so let me try this little trick of multiplying the amount of atoms of each side. Keep in mind, this trick doesn't always work, but it's worth a try, especially with a simple equation. So let's multiply 4 times 1, and this is going to give us 4. Then we add the 4 to one of these 2 places, so it can manipulate the number of phosphorus. I'll add it here. And this gives me 4 phosphorus on this side. Also, remember you have a coefficient. That number is multiplied by every single element in the compound. So we also multiply this 4 by 5 chlorine, and we'll get 20 chlorine. Now that our phosphorus is all balanced out, let's look at chlorine. We now have 2 on the reactant side and 20 on the product side. What can we add in front of the chlorine to make it 20? Well, we can add a 10, and then 10 times the 2 will give us a total of 20 chlorine atoms or moles. Awesome, so we're all balanced out here. Let's go ahead and move on to one more practice problem. Nitrogen plus hydrogen yields NH3. On the reactant side, we have 2 nitrogen and 2 hydrogen. I just want to emphasize that we have one compound with 2 different elements, both the nitrogen and hydrogen elements. Any coefficient that is placed in front of this compound will be applied to both, and in other words, the number will be multiplied by both the nitrogen and the hydrogen. The subscript 3, however, only applies to hydrogen. Remember, the subscript only applies to the element it's attached to. With that being said, we have 1 nitrogen and 3 hydrogen. If we place a coefficient of 2 here, we multiply it by both elements and we get 2 nitrogen and 6 hydrogen. How can we balance out this ratio of 2 to 6? We can put a coefficient of 3 here, and we get 3 times 2 hydrogen. We're left with 6 hydrogen. So everything is balanced out here. There is equal amounts of atoms of each element on both sides, as well as equal amounts of moles. Now, this can be a bit confusing if you're not sure what moles are, but just know that the amount of moles will be equal to the amount of atoms. Alrighty guys, so I have this last practice problem for you guys to go ahead and balance out on your own. I'll go ahead and have the answer for you at the end. There are 5 types of chemical reactions we're learning about today. The first is known as combination or synthesis reaction. In this reaction, we begin with 2 or more reactants and end with one product. In generic form, this can be written as A plus B yields AB. So we can see that both A and B combine together to make AB. A plus B are our 2 reactants and AB is our product. Next, we have decomposition, which can also be called desynthesis reaction. Here we begin with 1 reactant and it is broken down into 2 or more products. This is basically the opposite of synthesis reaction. In synthesis, we are building, and here in desynthesis or decomposition, we are breaking down. The generic form can be written as AB yields A plus B. Notice here AB is a compound and it breaks apart into 2 smaller components or 2 smaller elements represented by A and B. It is also important to know that most decomposition reactions need heat in order to break apart. Next, we have single displacement, which is also referred to as single replacement. Here, one element is replacing another. We can represent this with A plus BC yields B plus AC. Here the element A is replacing the element B. So in the product side, we will see they switch places. I like to think of it like people dancing on the dance floor. There is one single person dancing and a couple dancing together. Then the single person comes in and takes the place of one of the partners. And now that partner is dancing single or dancing alone. So basically they just switch places. Next we have a double displacement, much like single replacement, except here we have 2 elements replacing 2 other elements. This is the generic form. AB plus CD yields AD plus CB. Make note that in most compounds, there is a pair of positively charged and negatively charged elements. So we must be able to combine these in a way that we end up with a positive and negative pair. So here's how we're going to do that. We're going to combine the outer 2 elements, and then we're going to combine the inner 2 elements. As you can see, all pairs are nicely balanced with a negative and positive charge to each compound. So just remember, in a double displacement, combine the outer two elements and the inner two elements. Lastly, we have our combustion reaction. Here, a substance reacts with oxygen gas and it releases energy in the form of light and heat. In a combustion reaction, we must have O2 as one of the reactants. So we always have O2 in our reactant side and some other reactant. And this is going to yield most commonly CO2 plus H2O. So if you see CO2 and H2O in your product side, you can guess it's going to be a combustion reaction. Okay, so we've gone over all 5 types of chemical reactions: combination or synthesis, decomposition or desynthesis, which is the opposite of combination, single displacement, where one element replaces another, double replacement, where 2 elements replace 2 others, and combustion, where we end up with CO2 and H2O. So let's go ahead and do some practice problems. Here we have 2 elements on the reactant side that combine to make one product. Can you guess what kind of chemical reaction we have here? You guessed right, this is a combination or synthesis reaction. Next, we have 2 compounds that are combined to make one large product. Can you guess what kind of chemical reaction this is? Awesome, this is also a combination or synthesis reaction. Next, we have 1 compound and it is broken down into 2 smaller components. What kind of chemical reaction is this? Awesome, this is a decomposition or desynthesis reaction. Next, we have 2 compounds and it looks like they made 2 other different compounds. So what has changed here? Well, we can see that the outer 2 elements have combined and the inner 2 elements have also combined to create the product. So what kind of chemical reaction is this? Next, we have 1 element and 1 compound that yield 1 compound and 1 element. What do we notice here if we look closely? We can see that hydrogen has switched places with copper. So one switcheroo means we have a single displacement reaction. Okay, so now's your turn. You guys are going to go ahead and try the rest on your own. So how do we identify an acid and a base? Well, the answer is not so black and white. There is no definite way to identify an acid from a base without some hints, given like a chemical equation or some characteristics of a solution given. However, there are some helpful hints that, although not always work, they are very helpful. Acids are likely to begin with a H, and the H, or hydrogen, is attached to a non-metal. So, for example, hydrofluoric acid, hydrogen sulfate, hydrogen chloride, nitric acid, phosphoric acid, while bases are likely to have OH in them and or a metal attached to a hydrogen. So, for example, sodium hydroxide, potassium hydroxide, sodium hydride, and notice our sodium hydride does not have OH in it, but it does have a metal attached to a hydrogen, and that's what makes it a base. Calcium hydroxide is another example, and strontium hydroxide is another example. There are 3 important theories that can help identify an acid and a base. However, we are only going to emphasize on 2 of the 3 theories, those being the Arrhenius Theory and the Bronston-Lary Theory, because these are the only 2 theories I've seen on the practice questions for the practice TEAS exam. Now, if you happen to be watching this video and you're enrolled in a high school or college chemistry course, you will need to know the 3rd theory, which I will touch on later. The Arrhenius theory states that acids release hydrogen ions in a solution and bases release hydroxide ions in a solution. Bronsted-Lowry theory defines acids as proton donors and bases as proton acceptors. That third theory that I mentioned, for those of you who are enrolled in high school and college chemistry, is the Lewis theory. The Lewis theory states that acids will accept a pair of electrons and Lewis base will donate a pair of electrons. One helpful hint to remember before we go into these practice problems is that a proton is basically a hydrogen ion, or a hydrogen ion is basically a proton. This is because a hydrogen atom originally has one proton and one electron. So when it becomes an ion or a cation, it loses one electron and it's only left with one proton. So in essence, a hydrogen ion is pretty much just a proton. Okay, let's go ahead and look at some examples. Our first example is going to be on the Bronsted-Lowry theory. Remember, acids are proton donors and bases are going to be the proton acceptors. In this example, we have NH3, and we see on the solution side, it turns into NH4+. So NH3 has gained a hydrogen ion. In other words, it has gained a proton, because remember, proton is equal to hydrogen ion. So this makes NH3 the Bronsted-Lowry base. Because remember, by definition, bases are proton acceptors, and NH3 has accepted a proton or gained a proton. Let's take a look at H2O. H2O turns into OH negative, which means that H2O has lost a hydrogen ion. In other words, it has lost a proton. This makes H2O the Bronsted-Lowry acid, because remember, by definition, acids are proton donors. There's one more step we need to look at. Bronsted-Lowry bases will always create a conjugated acid. So here, the conjugated acid is NH4+. And acids will always create a conjugated base. So here, the conjugated base is OH negative. Okay, let's go ahead and move on and look at an example of our other theory, the Arrhenius theory. Remember, Arrhenius theory states that acids release hydrogen ions in a solution and bases release hydroxide ions in a solution. In this example, HCl breaks down, or in other words, dissociates into hydrogen ions and chlorine ions. What we're really interested in here is the hydrogen ions in the solution, because by definition, acids release hydrogen ions in a solution. So that means that HCl is our Arrhenius acid because it created or dissociated into hydrogen ions in the solution. Okay, so I just want to touch on something just a tiny bit off topic, because this particular chemical equation is very important for your TEAS exam. So on the top here, I have the exact equation that we just looked at in our example. HCl dissociates into hydrogen ions and chlorine ions. On the bottom, I have a more detailed chemical equation that includes H2O and H3O+. H3O+, by the way, is hydronium. Now, on your TEAS exam, or maybe another resource that you might look into, you might see this top equation or you might see the bottom equation, but just know that they both mean the same thing, and you must be able to recognize it and describe what is happening here. Basically, when hydrogen ions dissociate in water, they become hydronium ions. So really, you're not going to see hydrogen ions by themselves in a solution. You're going to see hydronium ions. So just keep in mind that H+ and H3O+, they are not literally the same thing, but they're pretty much the same thing. So keep that in mind. Okay, on to our next example. Okay, so here we have NaOH, and it's going to dissociate into sodium ions and hydroxide ions. Now, the hydroxide ions in the solution is really what we're focusing on and we're interested in, because by definition, bases release hydroxide ions in a solution. So because NaOH created or released these hydroxide ions in the solution, that makes NaOH the Arrhenius base. So here is a quick summary of the two theories that we just went over, and we looked at one example of each of these. Let's go ahead and move on. Strong acids and bases dissociate or ionize completely in a solution. For example, hydrochloric acid is a strong acid. It is found in our stomach and aids in digestion of proteins. I just want to emphasize that hydrochloric acid is an example that the TEAS loves to use often. So make sure you know what hydrochloric acid is and what the molecular formula looks like. So this is the chemical equation we're going to be working with. If you look closely, notice that HCl, or hydrochloric acid, dissociates completely apart. The hydrogen is donated to H2O, and that becomes H3O, and the chlorine becomes a chlorine ion all by itself. So because hydrochloric acid dissociated completely, that is what makes it a strong solution. But now, how do we know HCl is an acid? Well, HCl lost its hydrogen, or donated its hydrogen, and that's what makes it an acid. Let's look at another example. Sodium hydroxide is a strong base. In this chemical equation, sodium hydroxide dissociates into sodium ions and hydroxide ions. Because sodium hydroxide completely dissociated, it completely broke apart, that's what makes it a strong solution. Now, what makes NaOH a base? Well, it created hydroxide ions in a solution, and the Arrhenius theory states that bases produce hydroxide ions in a solution. So sodium hydroxide is a base, and it is a strong base. Now, completely opposite of strong acids and bases, we have weak acids and bases. Weak acids and bases dissociate or ionize only partially or not at all in a solution. Let's look at an example. Acetic acid is a weak acid. In this chemical equation, notice that acetic acid did not dissociate completely in the solution. It basically only lost its hydrogen ion and it kept the rest of the molecule intact. So because it didn't dissociate completely, it didn't break apart completely in the solution, that makes it a weak solution. Now, how do we know acetic acid is an acid? Of course, we can know it's an acid by its name, but what if we just saw its chemical formula? What if we just saw this chemical equation and not a label on acetic acid? How would we know it's actually an acid? Well, notice that acetic acid lost a hydrogen ion in its solution. And by the Bronson-Larry theory, an acid is one that loses a hydrogen ion. So one last thing I want to mention while using this exact same example is notice these double arrows going in opposite directions. This means that the chemical equation is reversible. If a solution is able to be reversed, assume it is a weak solution. Strong solutions are not reversible. Okay, so finally, what does all of this have to do with the pH scale? Well, the basics of the pH scale state that anything below 7 is an acid and anything above 7 is a base. And of course, 7 itself is neutral. The further you go up the scale and the higher the number, the stronger the base will be. And the lower you go on the scale and the lower the number, the stronger the acid will be. pH stands for potential of hydrogen. However, I like to think of it as a concentration of hydrogen because concentration helps me understand the definition better. More in depth, it really means the concentration of hydronium ions and hydroxide ions. Because a solution will either have more hydronium ions or it will have more hydroxide ions, meaning it will be more acidic or more basic. Your basic solutions will have a higher concentration of hydroxide ions, and your acidic solutions will have a higher concentration of hydronium ions. Okay, let's look at an example using hydrochloric acid. So here we have a flask with some H2O molecules in it, and we're going to add some hydrochloric acid, represented by these molecules. Remember, these molecules are representing our sample here. Because hydrochloric acid is an acid, we expect it to create a high concentration of hydronium ions in the solution. So if we take a close look, we'll notice that H2O is actually attracting that hydrogen atom away from HCl. So that hydrogen is actually going to detach itself from chlorine, and it's going to make its way over and it's attached to itself to H2O. And obviously this is going to create H3O plus or hydronium ions. So H3O plus or hydronium is formed, and now we're going to have a high concentration of H3O plus ions in this solution. Because hydrochloric acid is such a strong acid, we know that it's going to dissociate completely. So it'll look a lot like this in the solution. So that was an example of an acid. Let's look at an example of a base using sodium hydroxide. Here again we have a flask, and again we have some water molecules inside, and we're going to introduce some sodium hydroxide. Because sodium hydroxide is a base, we expect it to create a high concentration of hydroxide ions in the solution. If we take a close look at the sodium hydroxide, we'll notice that OH is actually going to dissociate or separate itself from sodium. And basically, sodium and OH are going to separate, and they're going to form free ions. The result is a high concentration of hydroxide ions. Because sodium hydroxide is such a strong base, it's actually going to dissociate completely inside the solution. So it's going to look a lot like this. So there's one last thing I want to mention here, very important. I wrote down here that acids have a higher concentration of hydronium ions. However, if you remember, our cat mentioned that hydrogen ions are pretty much the same as hydronium ions, because hydrogen ions, when they're in a solution, they turn into hydronium ions. So again, although it's not technically the same, it's pretty much the same thing. And I just wanted to mention that because if you look at another resource and they tell you the definition of pH, they might say that the acids have a higher concentration of hydrogen ions. But you know it's going to be okay because you know that hydrogen ions and hydronium ions are pretty much the same thing. Okay, so we've looked at an example of acid using hydrochloric acid, and we've looked at an example of a base using sodium hydroxide. And we know that pH stands for potential of hydrogen. In other words, we can also say that it's the concentration of hydrogen ions or hydronium ions, same thing, and the concentration of hydroxide ions. This sums up this video. I hope you learned something new, and thanks so much for sticking around, guys. Until next time.